Okay, everybody. This supplement is going to be a pretty short supplement, just finishing up one problem from the end of the lecture from 14.7, example 6 here. So this example is on finding the maximum volume of a box inscribed in a tetrahedron bounded by the coordinate planes and the plane 1/3 x plus y plus z equals 1. So let's start by sketching this. So we have our three coordinate planes. Let's try to see where this plane 1/3 x plus y plus z equals 1 intersects the others. So on the z-axis, when x and y are 0, z is going to be 1. When x and z are 0, y is going to be 1. And when y and z are 0, x is going to be 3. So I see that this is kind of my region that I'm looking at here. And then I have a box that has one corner at the origin and one corner on this tetrahedron. I'm trying to draw it somewhat convincingly here. So we have a box like this. So it's got one corner at 0, 0, 0, and one corner at, say, x, y, z. And we want to find the maximum volume of such a box. So as we move this point x, y, z around on the tetrahedron, the box might get longer in one dimension and shorter in another one. And for some x, y, z, we expect that there's going to be a maximum volume for this box. We can think of z as a function of x and y. So we can consider our domain to be in the xy plane. And I notice that this point here is at y equals 1, and this point here at x equals 3. So I'll take this triangle along with its boundary to be the domain D, over which I'm searching for the largest volume of this box. Okay, so I have to decide on an objective function that I want to maximize. So v as a function of x, y, z is, well, if I have one corner at 0, 0, 0, the other at a point x, y, z, this is just length times width times height, or that's just x times y times z. I would like this to be a function of two variables, x and y, so I can use all of the material that I just covered in 14.7. So I'm going to use the constraint from the plane up here, that 1/3 x plus y plus z has to be 1, solve that for z and plug that in here. Or that will be 1 minus 1/3 x minus y. So what is my goal? My goal is to maximize v of xy equals x times y times 1 minus 1/3 x minus y on this region D. So again, what do I have to do? Well, first I search for critical points and evaluate v at the critical points. And then I search along the boundary for maxima. And then I look for my maximum output and its location. Okay, so let's take Vx and Vy. I think it might be nice to write V in a little more convenient way. So let's distribute things here. V of xy equals xy minus 1/3 x squared y minus xy squared. So partial of v with respect to x is going to be y minus 2/3 xy, and then minus y squared. We want this to be 0. And then partial of v with respect to y is going to be x minus 1/3 x squared, and then minus 2 xy. And I want this to be 0 as well. I can factor this, so I get y times 1 minus 2/3 x minus y equals 0, and x times 1 minus 1/3 x minus 2y equals 0. And let's take x and y to not be 0 here, because if x is 0, I'm on the y-axis, and if y is 0, I'm on the x-axis. That's on the boundary. I'm going to handle the boundary in step 2. So I'll take x not equal to 0 and y not equal to 0. So this gives me two equations then. 1 minus 2/3 x minus y equals 0, and 1 minus 1/3 x, let's say 2/3, just written very messy, minus 2y equals 0. So I need to solve these two equations and two unknowns. I'll leave this as an exercise, but we get x equals 1, y equals 1/3 as our one and only critical point, and v at 1 comma 1/3, just evaluating this function for x equals 1, y equals 1/3, is going to be 1 times 1/3 times 1 minus 1/3, and then minus 1/3 again. Or this is 1/9. So that's my potential maximum value and its location. But again, I also have to check the boundary, because I could get a larger potential maximum value along the boundary. So if we look at the boundary, we see we have 3 line segments. We have one where x equals 0 and y ranges between 0 and 1. We have one where y equals 0 and x ranges between 0 and 3. And then we have this third one that's the line connecting these 2 points, 0, 1, and 3, 0. So this is the line when z equals 0. That's just 1/3 x plus y equals 1. In other words, that's the z equals 0 line for this plane. So v of 0 comma y, well, when x is 0, v, of course, is 0, right? Our box has 0 dimension in the kind of coming out towards us direction. So v of 0 comma y equals 0 for any choice of y. And same with v of x comma 0. When y equals 0, our box has no width, so the volume is also 0. And v at whatever point along this line, I'll just call it P. Well, here, what does this mean? It means that we have chosen a point XYZ along this line here. That's the top corner of the box, but that means the box has 0 height, because along this line, z equals 0, or that's when this bit here equals 0. So for any point along this line, my volume is also 0. So these would be the other three potential maxes that I would have to consider. But of course, with them all being potential maxes of 0, they're all beaten out by the maximum volume of 1/9. And I can now confidently say that I have an absolute maximum volume of 1/9 of whatever cubic units I'm using. And that's at location x comma y equals 1 comma 1/3. And I should use dimensions. X equals 1 unit, y equals 1/3 of a unit. And what would z be? Well, z would be 1 minus a third x minus y, or that's 1 minus a third is 2/3. That's 1 minus 2/3, 1/3. So these should be the dimensions of the box that I make that will yield an absolute maximum volume of 1/9. Okay, so again, pretty short supplement. That was all for this one. I just wanted to do one example of an application problem so that we could see how setting up an objective function and using the constraint equation might look.